Now our next topic in revision in isomerism after structural is geometrical isomerism. Remember one thing, we are doing revision. That means you keep your notes ready. Module if with you can keep your module also ready. I'm telling you certain things. Then you can do more examples. Okay, it's not about that we are starting from the scratch. It's like a quick revision so that in this time of lockdown you can utilize this time simultaneously by quick revision in the video format and then quickly revising the module questions that you have solved, and even in the notes you have done several examples. Okay, starting with the geometrical isomerism. Firstly, how we define it: compounds having same molecular formula, same structural formula, but differ in their arrangement of groups or atoms in space due to restricted rotation. That is geometrical isomerism, or these are termed as geometrical isomers. Then the conditions that required to show GI, geometrical isomerism, I will use now GI. Firstly, restricted rotation has to be there. Restricted rotation means either carbon-carbon double bond, because if single bond is there, and attached groups are like this, they can easily rotate along the single bond. That's why in the classification I told in stereoisomerism, one is conformational isomerism, that are interconvertible. Why? Because there is free rotation. But configurational isomers are geometrical and optical, and they are non-interconvertible. So here we are talking about geometrical, in which there is a restricted rotation, which means either carbon-carbon double bond is there, or C double bond N is there, or other possibilities are there, or ring structures are there. In ring structure also we consider that CC bond is in restricted rotation because it cannot move freely. Ring will not twist like this. Then next is condition is the two groups at each end of restricted bond must be different. Two groups at each end of restricted bond must be different, and distance between these groups must change. So point is, two different groups and their distance must change at each end of restricted bond. For example, now in this part, now you understand it better like this. Firstly, restricted rotation is there, double bond is present, first condition, but it is not the only condition. First condition, restricted rotation. Then we check for the other part, that distance of the groups must change, which is possible if we have two different groups. On this carbon, two different groups are A and B, right? On next end, that is other carbon, two different groups are there, B and A, right? Maybe here also AB, here also AB. It's about at each end of the restricted bond there must be two different groups. Maybe these two groups may match with the other end, but on each atom carbon two different groups, AB, BC, CD, like this. We can put here CH3 hydrogen, possible. So if I write another possibility, I can mention B there, A there, it remains as it is. Now in this case you can easily tell, if the distance between A and A is x, now distance between A and A is not x, it is something else, maybe y, and x is not equal to y. So the distance between the two groups will change, and then this compound means is participating in geometrical isomerism, and distance is changing. Why? Because these are two different groups on each atom. So when you try to write another possibility, then the distance between the groups will change, and that means that this compound is showing geometrical isomerism. So first condition, restricted rotation. Second condition, at each end of the restricted bond two different groups are there. That means the distance between the groups will change, and this is showing geometrical isomerism. Like in this case, distance between AA is different in the other one. So these two are geometrical isomers. Now try these conditions in the examples. Example number 1. In example number 1, restricted rotation is there, but on this carbon there are two same groups, so no need to check other one. No need to check other one. This will not participate in geometrical isomerism, right? Then next, double bond restricted rotation. I am marking star for geometrical center, and each carbon, this contains H and CH3, means two different groups. Left also contains two different groups, H and CH3. So we can write two forms. One is cis, one is trans. Cis means similar groups on same side. Trans means similar groups on opposite side. In third question, double bond is present there, restricted rotation, but this carbon is having two hydrogen, and we know at each end there must be two different groups, so this double bond will not participate. Similarly, another terminal double bond will not participate because two same groups are there, but this is a geometrical center, double bond, restricted rotation, and there is one hydrogen present, two different groups on right side, two different groups on left side. This will show geometrical isomerism across this double bond, not across the terminal double bonds. Question number 4. Restricted rotation, then carbon contain hydrogen and deuterium, two different groups, left side also two different groups, it will participate. Then next, restricted rotation is there, right? Because C double bond N is present, and this carbon contains one methyl, one hydrogen, means with left side restricted and two different groups, with the right side nitrogen, one is OH. So remember it, one is lone pair, one is bond pair. It is also treated as two different group. Carbon contains hydrogen and methyl, two different group. This will participate in GI. Next question, double bond N. N contains lone pair and one hydrogen, bond pair. Carbon contains hydrogen and one this group. So this is a geometrical center. Similarly, on the other side, nitrogen, lone pair, bond pair, two different groups, hydrogen, carbon, hydrogen, and this group, means this will show GI. 7th question. In 7th, two different groups are there on nitrogen, CH3H, HCH3. On each nitrogen there are two different groups, but there is no restricted rotation, there is a free rotation, so it will not participate in geometrical isomerism. 8th question, double bond restricted rotation, carbon contains hydrogen and phenyl, two different groups, right? And here OH is there, one bond pair, and if you remember, if O is there, it means out of the two lone pairs, one is still present, that is lone pair and bond pair. That is the reason this will also participate in geometrical isomerism. In 9th, restricted rotation, triple bond, but there is only one group, and we want how many? Two groups. Why? Because then only we can write the structures where distance of the groups will change. So with alkyne, restricted rotation is there, but other conditions are not satisfied, so no GI with alkyne carbon. 10th, in ring structure, remember sp3 atoms if present, there are 4 sp3 carbon atoms, and then check at least for two carbons, maybe adjacent, maybe non-adjacent, two sp3 carbons, they should contain two different groups, at least two sp3 atoms, and they contains at least two different groups, then GI is possible in the ring structure. So here if you see this carbon, they are sp3, but they contain H2, CH2, no GI, but this carbon contains hydrogen and Cl. Another carbon also contains two different groups, hydrogen and Cl. So this is a geometrical center, and we get what are the possibilities? Both Cl above the plane, that is cis form, one Cl above, one Cl below the plane, that is trans form. So this is the GI possible. Then 11th, similar example, this carbon and this carbon contains hydrogen and methyl, it also contains H and methyl, so this will also participate in GI, geometrical isomerism. Example number 12th, Here only one carbon is sp3. If the carbons are sp3, how many? Minimum 2. Clear? Minimum 2 sp3 atoms, and they should contain 2 different groups. It will show geometrical isomerism. If there is a double bond, that means sp2 carbons are there, then always remember the size of the ring should be 8 membered or more. Then only ring can flip, otherwise there will not be possibility. So in this example number 12, there is a double bond. So along double bond there is no possibility because size of the ring should be 8 or more, and there is only one sp3 carbon which is one sp3, and we want at least 2 sp3 carbons which contains 2 different groups. So double bond will not participate and there is no sp3 atom, so no GI in question number 12th. Then 13th. In 13th example, these terminal rings, they won't participate. Why? sp3 atoms are there but same group, CH2 CH2, and this is containing 2 different, that is 1 hydrogen, 1 this part, but we want how many? 2 sp3 atoms minimum. So terminal will not participate, but that ring contains hydrogen, this also contains hydrogen, H and ring structure, H and ring structure. So with respect to central ring, we will get geometrical isomerism, right? Then in next example, here ring structure, double bonds are present, but size of the ring is 6 membered. So along double bond, we will not check for GI, but we can try for sp3 atoms. How many require? 2, and they should contain at least 2 different groups. Now check. This carbon sp3 contains 1 hydrogen and 1 methyl. Exactly opposite contains 1 hydrogen, 1 methyl. Now this will participate along the first and fourth carbon, which is sp3. Then next example, along double bond, no GI, and all other sp3 groups, they contain CH2, so not possible. 16th is an example where 8 membered ring and double bond is present, so this will be participating along the double bond, because across double bond in ring structure, always remember that size of the ring, if it is 8 or more, then it will participate in GI. So these are some examples in geometrical isomerism. You can try more examples from the notes and module. Now next is example 17, in which we have to check GI. Now here restricted rotation is there. It is in double bond, it is also in ring structure, but in the ring carbon sp3, they have same groups attached, so we will not find GI along the ring structure. So we can check for that one, that here this carbon contains 2 different groups, but the carbon which is in the ring structure, it contains CH2 there, CH2 there, so no GI in the compound. 18th, restricted rotation, 2 different groups are there. With this carbon, 2 groups, but they are same. With this carbon, we have to check the center where we are trying. If we compare for this double bond, then at each end of the restricted bond, 2 different groups must be there. So on the left side, 2 same groups, so along this double bond we will not get GI, but this carbon is sp3, contains 2 different groups, one is CH3, one is hydrogen. This carbon also sp3, contains 2 different groups, H and CH3. So along the ring structure we are getting GI, not across double bond. You got that one? Then next is 19th. Here double bond, restricted rotation, carbon is containing H and methyl. Then check with the carbon in the ring. Here CH2, there is not CH2, it is CH3. So this will be the for satisfying the condition. Now from 20th onwards, it is a slight different case. So I'll simply say you the point, theoretical point, in your notes also it is there, that these are examples of allenes. In allenes, double bond, cumulated dienes are known as allenes, right? Now they can be even numbered or odd numbered. So I will not answer it through hybridization and drawing the structure, because this will be complicated also, and we'll do simple method. That is, this is even numbered alene, and in even number the terminal carbon groups are H and Cl on right side, H and Cl on left side. They are in different plane. The terminal groups HCl, they are not in the same plane, they are perpendicular to each other, and if they are perpendicular to each other, the distance between the groups will never change. Whatever configuration you try, if they are perpendicular, there will be no geometrical isomerism. So that is the way we easily find out if the summation is even number. Terminal groups groups will be in different plane, and there will be no geometrical isomerism. So these are some different cases. So we cannot directly use the point, restricted rotation, this, that, because we should know these examples first. Now next example is not even numbered. It is alene with odd number of double bonds. So we will check the terminal groups. They will be in the same plane. The terminal groups will be in the same plane. Then should check that the terminal groups or carbon contains two different groups. Like here, two different groups are H and Cl. There is H and methyl. Now firstly, that is odd number, so terminal groups are in same plane. Second is the terminal carbons, they contains two different groups, then it will show geometrical isomerism. If there are same groups attached, then it will not participate in geometrical isomerism. Question number 22. Similar to alene, you can understand it. Continuous ring structure. How many? 2. 2 means we can take again even number. Then at the extreme ends. Extreme ends are these two. Extreme ends, terminal carbon, the groups are H and F. H and F. They are in different plane. So no geometrical isomerism. But in next example, continuous ring structures. That is the case of spiranes, even odd number spirane, terminal carbons or extreme ends are these two, and they contains two groups. That means they are in the same plane. Now check whether the two groups on each carbon are different or not. So here two different is there. One is hydrogen, one is fluorine. Other is also two different. One is hydrogen, one is fluorine. So it will show Gi. 24th. Here summation is what? Odd, alenes. It means terminal groups are in same plane. Then check at the terminal or the extreme ends, two different groups has to be there. Here two different groups, yes, H and Cl. There is H and H, that means same group, so it will not participate in geometrical isomerism. Then E and Z configuration, because cis and trans we use when there is a similar type of group. Similar groups on same side cis, similar groups on opposite side trans. But EZ is the configuration where we can use for IUPAC nomenclature also, EZ configuration. E means the same priority group. Priority, I am using the term priority. Same priority groups on the opposite side, they are termed as E configuration. And if on the double bond, same priority groups on the same side, then this is termed as Z configuration. E means opposite, Z means together, and we will set the priority. Now, how will we set the priority? There are rules which are CIP rules. Firstly, with respect to the geometrical center, we go for atoms connected. Higher is the atomic number of the first atom. We move from the double bond both sides and check both sides. The first atom which has higher atomic number will be getting first priority. If the atoms are same, then we move on to the next atom and check their atomic numbers. If there are different isotopes, then heavier isotope will be considered in more priority. Then bond pair and lone pairs are present on the atom, then bond pair should be having more priority as compared to lone pair. You can understand this part by examples. Now this is restricted rotation, this is our geometrical center. Two different groups, that means it will participate in geometrical isomerism, then only we check for E and Z. If geometrical isomerism is not there, there is no use of E and Z. Now here right side, first atom is oxygen, first atom is carbon. No need to think about IUPAC priority. It is CIP rule where it is mentioning clearly, we check for the first atoms both side here. Which is having higher atomic number, we will give it more priority. If atomic number same, then move on to the next atom. Similarly, next atom till you are getting first difference. So here oxygen, carbon. So oxygen means more atomic number, first priority on the right side for OCH3 group, second for carboxylic. Similarly, on the left side, first atom N, first atom Cl. First atom Cl, that more atomic number. Now 1 and 1, same priority on the same side is Z configuration. In second example, these two will not participate. It will not show GI, only this one will participate. Now, what is the groups present? H, H. Now give the priority. H and carbon, which is first 1, 2. Similarly there, 1, 2, 1 and 1 opposite side. E configuration. Next example. Geometrical center is there. On the left side, deuterium and hydrogen. Heavier isotope will be first and then hydrogen will be second. On the right side, N, OH and lone pair. Then we consider bond pair and lone pair. Bond pair will be first, lone pair will be second. 1 and 1 on the same side. Z configuration. I hope you are getting. You will try more examples. Next, on the left side, ring structure. Carbon is there, hydrogen is there, first, second. Here oxygen, there is carbon, oxygen. 1 and 1 opposite, E configuration. Done? So at least you should do simple examples, not very complex examples, simple examples to understand the concept. Okay? Now next are some general comparison of physical properties among geometrical isomers. Like here in the example, both CH3 same sides, it is cis form. Both CH3 opposite side, it is trans form, right? So if we compare their dipole moment, we know CH3 group electron releasing. The bond moments are like this. In trans form, bond moments are like this, electron releasing towards double bond, it is also towards double bond. So in short, we can say that trans dipole moment will be cancelled and cis will not be cancelled. So cis here in this example, cis will be having more dipole moment as compared to trans. So here we can compare mu will be more for first structure as compared to second. Now generally boiling point is directly proportional to mu, because more is the dipole moment, more is the polarity of the molecule, more will be the intermolecular force of attraction, and hence more will be the boiling point. So we can compare in this example that one should be more than second. Why? Because general points, boiling point directly proportional to mu. Then next is melting point. Now melting point is not depending upon the mu, because melting point here simply means that more is the packing of the particles, better is the crystalline packing, higher will be the melting point. So remember one thing, that trans isomers are more symmetrical as compared to cis isomers. Therefore their packing is very efficient and hence their melting point is more. So in melting point we can go for trans better than cis. Then solubility, again directly proportional to mu. Solubility in water we are talking about, therefore which is more? First is more than second. Now we can add one more point, that is stability between them. So between 1 and 2, trans isomer is more stable. Why? Because bulky groups are on the opposite side, so very less force of repulsion, van der Waals force of repulsion. Whereas in cis, bulky groups are on the same side, more repulsion and less is the stability. Similarly, you can try next example. You can pause this video, you can try that example, then check your answers. In example number second, Br is there, CH3 is there, CH3 towards double bond, Br is electronegative towards Br. Same way here in second structure, which is trans form. Now in this case, the trans should be having more dipole moment because it is net resultant is towards one side, and here it is less as compared to second. So you can start with that. Between 1 and 2, second is having more dipole moment. Then boiling point, again we can go for that between 1 and 2, second should be more because of more dipole moment. Boiling point should be more due to more force of attraction between the particles. Then melting point, same point, like trans isomers are more symmetrical and there is better crystalline or better packing efficiency in that trans isomer. Then in solubility, again here second is more. Why? Because of more dipole moment. And if we talk about stability, again second will be more than first. So in this example, all properties are second more than one. That's why I say it depends on the example taken. Clear are the examples? Then next is the question. You can write it in your rough notebook quickly and then you can try it. That question is, which of the following compounds will show geometrical isomerism after reaction with NH2OH? Which of the following compounds will show geometrical isomerism after reaction with NH2OH? Now if you see the examples or the options or the examples given here, they all are carbonyl compounds. So in this part you can use which theoretical point? You can easily use one point, which is that in carbonyl compounds we have done example of oxime formation. Carbonyl compound treated with ammonia derivatives. Among ammonia derivatives, one is NH2OH. So I am using that reaction, which is with NH2OH. If we treat, we get one oxime compound. We have to check whether this oxime is giving GI or not. So you have to write every question till G. Write down the oxime formed and check whether GI is there or not. Okay. So I am starting with the first one. You can pause this video, you can try on your own, then you can check the answer. Now starting with the first one. After reaction with NH2OH, the oxime formed in 1 is this. Now you can tell it whether this will show GI or not. It will not show GI clearly. Why? Because the carbon contains two same groups. So here you can merely check it if the carbon of carbonyl is having two same groups. It will not show GI after reaction with NH2OH. So no need to check every time, but if you practice, you can try some of the examples. In second example, carbon contains two different groups, because we know after the reaction it will form what? After the reaction it forms oxime and end contains one bond pair, one lone pair. So this end is having two different groups. Only we should be confirmed that this end should be having two different groups. Okay. So in this case, first one will not, but second one will participate. Now what about third one? In third one, you can directly find out that carbon contains two same groups, so the oxime will be formed. It will not show geometrical isomerism. In next one, carbon contains two groups and both are different. One is H, one is deuterium, that is isotope. These are considered to be two different groups. So this will show geometrical isomerism after reaction with NH2OH, or this product oxime will be showing GI. In next example, carbon contains two different groups, so oxime which is formed will not show any geometrical isomerism. Then next example, this one, it is also very easy example. When you try, if you want to try, you can try it like that. This carbon contains two same groups, then move further to again same groups. It is treated like that, it will not show any geometrical isomerism. How to check? With that carbon, both sides CH2, move further, both sides CH2, no difference. In next example, if you write the product will be like this. And on the either of the side you can mention that. Now, double bond, two different groups. Now with this carbon, adjacent is CH2, but here it is different, it is CH. That means these two are different groups, and the oxime formed by this compound show geometrical isomerism. Now if you have tried that question, the answer is among them which will show second, then fourth, then seventh. Out of these compounds, three are showing, three oximes will show geometrical isomerism.